So as she said, this is a talk nitpicking textures, programming and modifying complex knitted textures for hand and machine knitting. I'm Megan Hofmann, and I'm presenting this on behalf of my co-authors, Leah Albaugh, Ticha Sethapakadi, Jessica Hodgins, Scott Hudson, James McCann, and Jennifer Mankoff. And I'm going to put on my accessibility chair hat on real quick. If anyone wants to see captions for this talk or any other talks in this room, you can find them at this URL, tinyurl.com/swishsouth. All right. So as you might have guessed, this is a talk about knitting, and this might be what you picture when you think of knitting, but instead we're mostly going to be talking about this kind of knitting. This is an industrial knitting machine that we have at the textiles lab at Carnegie Mellon. And industrial knitting is a very robust and mature technology. In fact, everyone in this room is probably wearing something that was made on an industrial knitting machine very similar to this one. So you might be wearing a sweater, though it's a little warm in New Orleans. Better odds are that you're wearing socks. Those were probably knitted by a machine. And it looks something like, there we go, something like this. These are pieces of technology that are used on factory floors across the world, and as a result, the interfaces for them are a little bit poor. They're not really designed for kind of rapid prototyping or thinking through interesting fabrication problems. They're designed to create one product which you make 1,000,000 times with a lot of upfront effort. And what gets me really excited about industrial knitting or knitting machines is that they can produce all of these really interesting textures with all of these really cool physical properties. So they can be stretchy, they have all these kind of diagonal features to them, they can be lacy. And as my co-author Leah Albaugh showed us at Chi earlier this year, if you start to play with the physical properties of these different textures, you can create all sorts of interesting physical objects. So you can create something like this lamp, or this very attractive sweater, which will pop up. There we go. Love that one. So let's say you want to get started with your own industrial knitting machine. Well, you're going to have to learn a piece of software like this. And if you're expecting me to explain what's going on in this picture, I have to tell you I have no idea. There might only be one person in this room who could figure it out. That's my co-author. But this is what the industrial tools look like. But there have been some recent advances in the area. So back in 2016 at SIGCHI, people from our team started to work on a compiler for 3D knitting, and they said there are basically 4 basic operations that control these machines, and you can treat those operations as kind of the assembly language of knitting. And once you have an assembly language, you can start to build algorithms on top of that to deal with things like shape. So you can take a 3D model of this famous Stanford bunny and then produce something that will produce the skin of that bunny out of a knitted object. But there really hasn't been that much focus on texture because these textures change the physical properties of knitted objects, and as a result, the shape is going to change of what you're producing. Earlier this year at SIGCHI Asia, there has been some work on applying textures on top of these, but they're still kind of treating them as 2 separate problems, adding the texture on top of the shape later. But there are lots of people who understand how knitted textures work. They're called hand knitters, and they do this on a fairly regular basis. So how do they understand knitted textures? Well, they understand them in very much the same way as a person or as a computer might. They understand it as a series of instructions that they write out in this language right here called KnitSpeak. There's a few different dialects of this, and every knitter has their favorite. And then often they'll kind of visualize them with charting tools like the chart shown here and then the representative sample to understand how it's going to look before they go through the process of hand knitting. So we looked at this very pragmatic language, and we said, well, let's build a compiler. So we wrote a compiler that can compile 2 different versions of KnitSpeak that are very similar. One is the Essential Stitch Collection by Stanford and Griffiths, and the second is Stitch Maps, which is an online open repository by J.C. Breyer. And we have compiled to date and measured 300 different samples. Here are a few of my favorites. But if you're thinking about this as a compiler, you have to compile down to some kind of representations. And in order to understand that representation, I'm going to have to teach you a little bit about knitting. This is a loop of yarn. And if you were to pull on the 2 tails of this yellow loop of yarn, you no longer have a loop of yarn, you just have a strand. But if you pull that loop of yarn through another loop of yarn, that bottom green loop of yarn now, if you pulled on those tails, it would be stable. You'd keep that loop. So we call this the loop-to-loop constraint, that all loops pulled through other loops stabilize the first loop. And you can start to play with this. You can pull them from the back to the front, which is called a knit, or you can pull them from the front to the back. We call that a purl. And so now you've got two different pieces of texture here. And you can pull more than one loop through a single loop, which creates a decrease. That decreases the number of loops you have available to you, the yellow ones. Or you can add a loop that you're going to have no parent to, and that we call that an increase or a yarn over, which increases the number of loops that you have on a row. And if you pair these decreases and increases together, you get kind of like a hole in the fabric, and that's how we make lace. And then you can also cross these loops one over the other, so you have kind of a three-dimensional feature here, and we call this cabling, or traveling stitches, colloquially. And this gives a very interesting kind of springy effect to the fabric. And if you're thinking to yourself now, we've got these different kind of nodes connected to other nodes. That sounds like a graph. Then you know where I'm going next. We call these KnitGraphs, a time-ordered collection of loops pulled through other loops. So you can think of the green edges here as the yarn of the fabric, connecting all of the loops that are made one after another. And then the purple edges are connecting them where you're pulling one loop through the other. And as long as you have 4 properties, but primarily that loop-to-loop constraint meant, you're going to produce a graph that would result in a viable knitted object. All right, so now we've got a compiler, we have something that we can compile down to, and then we have actually 2 different output products where we can create instructions for an industrial knitting machine, or you can create hand instructions so that someone can knit these different samples by hand. But we don't really want to stop at just representing a single texture. We want to say, well, what if I want to change the size of that texture or shape it in some way? Or what if I want to combine it with 2 other structures? And to support that, we have 2 different optimization algorithms. I'm going to start with KnitCarving. And KnitCarving is for sizing individual textures. You can think of a texture as kind of like a tile that you repeat across a rectangular grid. So in this case, there's 4 repetitions of this lace structure. And if I want to say, like, cut into these textures to reduce the width in this case, then I'm going to have to think about that loop-to-loop constraint. Which loops can I remove before the thing unravels? So let's say I want to narrow this by just cutting off this edge right here. Well, the naive result is going to produce this hole where this fabric is starting to unravel as I touch it. So instead, let's think about this as a cropping problem or something like an image cropping problem. So if I have this representation here with all of the different stitches, and I decide that each of those stitches or loops has a cost to remove. If a loop is dependent on it, then its cost is infinite. The whole thing's going to fall apart if I remove it. But if it doesn't, then its cost is based off of its rarity in the sample. So the number of loops is a fraction of the total loops that make up similar stitches. So if I've got a lot of knits, then knits have a very low cost to remove. And if I've got very few purls, then purls have a very high cost to remove. And then once we've assigned this cost to each of these loops, we can find the minimum path using dynamic programming to kind of cut this nice diagonal or chevron pattern out of the texture and get something very similar. And when we do this on knitted results, we get something like this, where the one on the bottom left is almost indiscernible from the original texture, but I guarantee you it is 1 stitch narrower. And if I start to play with these samples and narrow selectively, starting at the bottom, only narrowing a little bit, and then narrowing as I go up more and more, you can start to shape or change the shape of the different knitted objects, which is how you get something like the hat I'm wearing and pictured here. But we want to work with more than one texture at a time. In this case, I actually use 2 different textures, one at the little rib at the bottom and then one at the top. But if I want to do that in a more complex way, maybe to create this panel here, we get this problem where it gets very lumpy. And it's because of all of those cool physical properties in knitted textures are different across those textures. And if you put 2 things that have different kind of stretches to them, they'll bunch up at the boundaries. And so you get something lumpy and not quite square. So how do we solve this problem? Well, we first start to think about the number of loops at the boundaries of these different patches, these different colored sections of the fabric right here. And we think about trying to balance those loop counts so that we reduce the error at those boundaries. The first source of error is sizing error, which is the idea that the number of loops is correlated to the width of the fabric. And so you have this idea of gauge, the number of loops per inch. And then you subtract that from the actual width that you're going to get, or the target width that you're going to get, and that is representative of the error that you're going to get from sizing. The next error that we get is texture error. So if I have to narrow this texture by less than a tile, I'm going to have to use KnitCarving, which will introduce some error into the texture. And so the number of removals, or that delta there, is going to increase the error of this fabric. And then finally, we can actually add edges in the graph at the boundaries. So we can have the number of loops at the top or bottom of this yellow patch be different than the number of loops across it by having increases and decreases. But those increases and decreases are going to create little eyelets that you can see, and so that's going to produce an error in the fabric. And so here's the end result, that we get this much more uniform and flat sheet of fabric, but you can even start to see where that joining error is coming in with those little eyelets. And this actually works on almost every texture in our database. We can see that this works pretty well across different kind of cables and different laces. In fact, those earlier samples, which are pretty basic textures, have the most divergent stretch, and so they're going to have the greatest effect. So some future work to think about in this space. Ideally, we wouldn't be working with a programming language for a user interface, and so we need to use this as kind of a jumping off point to build more graphical interfaces that might be more approachable for different types of designers. And then we further need to combine texture, shaping, and physical simulation so that we can really crack this problem of the shape and its relationship to the physical properties and the textures that it's built out of. And once we've done that, and while we're doing that, we can start to work on thinking about using tools like industrial knitting to produce more interesting, soft, functional objects. The kind of takeaways I want to leave with this talk are that machine knitting requires a design pipeline to support texture and shape. We've kind of started to approach that pipeline here, but I think there's a lot of room to grow here. And hand knitting instructions are actually a super valuable resource for knitting designs. There's lots of work that's already been done in this space outside of the industrial space, and so we can really rely on that boundary of knowledge to study knitting as a field. And then finally, sizing, shaping, and combining knitted textures poses new opportunities to design soft materials. So once we have kind of cracked this pipeline, we've built all of these tools, it's going to be much more accessible to start to play with this for things that are maybe a little more interesting than garments. Thank you so much. Are there any questions?
Thanks very much for that excellent presentation. Also very cool that you're wearing your own results from your paper. So we have a couple minutes for questions. Any questions from the audience?
So can you talk a bit about things outside of fabrics that you might think this texture and shape relationship might be important for?
You mean outside of the knitted space? So I think this work is very specific to kind of the knitted properties, and I had to kind of gloss over it for time, but we go into detail about those physical properties in the paper. I think outside of knitting, this is a challenge for other types of kind of textiles like woven materials or other types of ways of producing fabrics. I know some of the papers later are looking at 3D printing, and I'm sure they will attract some of the same issues. I'm not quite sure how the concepts that we've taken here will translate necessarily, but focusing on this idea that you can create these kind of like microstructures in this case and then apply them to change the physical properties is a space where optimization and different approaches are really applicable across the field. Whoever has the microphone. Oh, there we go.
Really interesting work. I really think it's cool. I have a question, though, of how do you envision the abstraction between moving away from an interface that's very much programmatic and like assembly into a more graphical interface? How do you envision that interface looking in terms of like how a designer would actually use it?
So there's actually a lot that I think we can start off with learning from kind of how hand knitters have hacked together charting tools. The Stitch Maps repository actually has a charting tool built into it that we looked at. And I think that kind of representation is maybe a good place to start. The challenge here is that if you draw something that you have as an intention for a texture and then you want to go back to this programmatic representation, that's clearly a little bit more difficult than going from the program to the representation or to the visual representation. I'm looking into some work on using program synthesis approaches to try and solve that problem, but I think there's a lot of challenges there that are unclear at this point. I think another approach that might be appropriate is to think about how do people kind of paint on what they want or what they expect from the fabric. So I want it to have cables, I want it to be lacy, I want it to stretch, and then use optimization approaches to learn from things like our data set and generate something as a result for that, and then work in kind of a mixed initiative approach until the user gets something that they really want.
Great talk. Thank you so much. I had a related question about moving into a graphic user interface. And it relates to who you are thinking about designing this for, because it seems like audiences who are already experienced knitters think about things algorithmically and programmatically and are used to dealing with something that is a programming representation or very similar to that, versus audiences who are maybe new to designing for knitting wouldn't be familiar with that space. So it seems like having a programming-based interface might be very appropriate for people who are experienced knitters. Can you talk a little bit about how you think about that trade-off?
I think it's hard because there are lots of people who can read these kind of knitting instructions, but I think it's much harder to find people who are used to writing them or would like to write them. We haven't really done any of the groundwork to kind of analyze how these communities produce things, so we could look at groups like Ravelry to see what knitters would want. And I think in some ways it's very different than industrial knitters. So industrial knitters use a completely different pipeline to define these textures than hand knitters. I think the graphics approach is probably better because we're still in that space where we're ultimately producing something that is very visual or physical. And so people are going to have an easier time understanding that if they're looking at what they're getting, rather than going kind of through this very laborious process of saying, I'm going to program this out, and then I'm going to make it or visualize it in some way, and then I realize it's not quite right, and then I go back and forth, and that process is very tedious, I can say, from even just making the demos in this paper.
Great. Thank you very much. Great question period, and let's thank Meg.